Okay, AP, here's your walkthrough for how you balance oxidation reduction reactions. And I'm going to show you some simple reactions first. This is on your handout. And these reactions you can actually balance without doing the method that I'm going to show you. But I'm going to show you the method because we're going to use it for more complex ones. So if you're going to balance an oxidation reduction reaction, there's really two things you want to look at. We want to balance every atom in the chemical reaction, and we want to make sure that we balance the charges, or the ions, or the number of electrons on both sides in every chemical reaction. So the number of atoms and the number of electrons. And to do that, we want to keep track of electrons. So we're going to assign oxidation numbers. Copper is 0. Silver is +1. Copper is a +2 on the product side, and silver is a 0. We can identify who's gained and who's lost electrons and figure out who's oxidized and reduced. And so the copper ends up being oxidized. Oxidation involves loss. Remember, oil rig. And it lost 2 electrons. It goes from a 0 to a +2 charge. And the only way you can get more positive is if you lose negative electrons. Your silver gains 1 electron, and we would say silver got reduced. And what we're going to do is we're going to separate these out into what we call 2 half reactions. So I'm going to take my oxidized part of my equation, and we call that the oxidation half reaction. That'd be my coppers. I'm going to take my silver, my reduction half reaction. That's the half the equation that involves gaining electrons. And we take everything that is a part of the oxidation and everything that's part of the reduction, and we write them in their own little half equations. So we take our copper and our copper +2. There's what's on the products and reactant side. And then my reduction half reaction, there's what's on my products and my reactant side for my original equation. And the reason we separate this out is to keep track of electrons. Once you have it separated out, you want to evaluate, do you have equal numbers of atoms in each of your half reaction? I have 1 copper on the left and 1 copper on the right, so we're equal in terms of the number of atoms. The next thing you want to evaluate is, do we have electrons balanced? And the way to figure out if your electrons are balanced is just add up your charge. So on the left side, we have a neutral charge, and on the right side, we have a +2 charge. I want those charges to be equal to each other, so I'm going to add 2 electrons to this side. And those electrons are the 2 electrons that were lost by copper. It starts out with all of its electrons. It ends up as copper with 2 fewer electrons, and we write that in an equation as 2 electrons, 2 extra electrons on the product side. This is now balanced in terms of atoms, and it's balanced in terms of electrons. We're going to do the same thing for the reduction half reaction. For silver, we want to check the atoms balanced. We have 1 silver on both sides, so our atoms are balanced. And then we're going to balance our charge. We're +1 on the reactant side, and we're neutral on the product side. And so we need 1 extra electron on the reactant side. And that would be gaining an electron to become silver neutral. And that's what we saw in our reaction up here. We gain 1 electron. Once both of your half reactions are balanced, we want to check to make sure these guys, your number of electrons that are transferred, are equal before we add these 2 equations back together to get our balanced overall equation. And to do that, all you want to do is figure out what's the least common multiple between 2 and 1. And the answer is 2. I just need to take my reduction half reaction and double it. I need 2 silvers, which will give me 2 electrons accepted. And if you double this reaction, we get something like this. 2 electrons plus 2 Ag plus turns into 2 Ags. And if you add these 2 reactions together now, the oxidation half reaction and the reduction half reaction, this is how you add reactions together. You take all of the reactants of both equations and you put them together in one big equation. So this is going to go together on the reactant side. I'm going to say copper plus 2 electrons plus 2 Ags turns into, and now I'm going to take everything on my product side. Let me switch colors here. All of these guys, and my 2 silvers here on my product side. And that ends up being Cu2 plus 2 electrons plus 2 silvers. And if you look at our equation now, there's something that's the same on both sides. We have 2 electrons on both sides. Those can cancel out. And it leaves us with our overall balanced equation, Cu plus 2 Ag plus turns into Cu2 plus 2 Ag. And this is balanced in terms of atoms. There's 1 copper on both sides and 2 silver on both sides. And it's balanced in terms of the electrons that are transferred. And all that extra work just to say, you could have just come up here and seen Well, we gain 2 electrons here and we lose 2 electrons here. It's pretty easy to see we just need 2 silvers so that we're gaining the same number of electrons that we're losing. And for simple equations like that, they can just be balanced like that. But we're going to use this half reaction for slightly more complex ones. So I'm going to show you another one here. If we're balancing our oxidation reduction reaction for this one, we want to do the same thing. We want to assign our oxidation numbers. Magnesium is 0. Hydrogen is +1. Magnesium is a +2. Hydrogen is 0. And then you want to evaluate who's oxidized, who's reduced. Magnesium goes from a 0 to a +2, so it lost 2 electrons. Hydrogen gained 1 electron, and so it's reduced. And we can write our half reactions. We just take out of our equation everything that was reduced for the reduction half reaction, everything that was oxidized for the oxidation half reaction, and we're going to do the same thing. So I'll walk you through it again here. And I won't write all of our steps, but we'll just write it out here. Magnesium, we have 1 magnesium on both sides, so we're balanced. If I want to balance my charge, I need 2 electrons on this side, so I end up with a neutral product side and a neutral reactant side. I'm going to do the same thing on my reduction half reaction. And the first thing you want to do is balance your atoms. We have 1 hydrogen on this side and 2 on the product side, so I need 2 of these guys, 2 H pluses. And now I'll balance my charges. And if you balance your charges here, we need to add 2 electrons to this side because we have 2 hydrogens each with a +1 charge, and that makes a neutral reactant side and a neutral product side. It doesn't have to be neutral, it just has to be equal in charge on both sides. And now if you compare these 2 reactions, the thing that we're looking at is our number of electrons. Are the number of electrons transferred the same? We're gaining 2 and we're losing 2. It is. We don't have to multiply by any multiple here for our half reactions. We can just add our half reactions together. And if you add your half reactions together, you get magnesium on your reactant side, plus from our reduction half reaction, we get 2 electrons plus 2 H pluses. Turns into, on our product side, Mg2 plus 2 electrons from the oxidation half reaction. And then we also get our H2 from our reduction half reaction. And it should always have your electrons cancel if you balance your equation correctly. And this would be your overall balanced equation. And again, this is a very simple one. This is one that you might be able to say, Mr. Robbins, why didn't we just go up to the top and balance it? This is balanced now. If we just go up to the top, if we saw that we lost 2 electrons and gained 1 electron, couldn't we just say we need 2 of these and now we're balanced? And the answer is yes, you can do that. But this method we're going to use on our next problem, and it's the best method for doing complex equations. Okay, so your next one, there's a bunch of steps for. You can cross this one off. This one shouldn't be in your packet. It's not a correct problem. Okay, so you can cross that one off. So here's your next one. Your next one asks you to balance this equation in acidic solution. You have a bunch of rules above it, and I'm going to use all those rules to balance this. But first I want to explain to you what we're doing and why. This type of chemical reaction is an oxidation reduction reaction. You can figure that out by figuring out your charges of, or your oxidation numbers for all your ions. Let's go ahead and do that and figure out what happens here. We have -1 for bromine, a -2 for manganese, or for oxygen in our permanganate, and this would be a +7. And you can do the math here. This is 0. This is +2. So we do have a transfer of electrons here. But why would we want to figure out how to balance this? And why is it so complex? You'll see why it's complex here in a second, or how complex it gets. But this is what's happening. This particular chemical reaction would be happening in solution. And so we've got this in a container back in lab. And the solution could be acidic or it could be basic. And if we're acidic, we have these guys floating around in solution, H pluses. Or if you're doing this chemical reaction in a basic solution, you have OHs floating around. Both of those scenarios could cause different interactions when this chemical reaction occurs. But if you notice here in our chemical reaction, we have oxygen on the left side, but we don't have oxygen on the right side. And that oxygen has to come from somewhere. So not only in our container do we have an acid or a base, we have H plus or OH floating around, we're also in water. And so we have H2O available. And these 3 compounds, H2O, an acid, H plus, or OH, depending on which solution we're in, acidic or basic, actually get to participate in the chemical reaction. And so we can be ripping apart H2O molecules to make H pluses or OHs, or it could be using up some of our hydroxides or our protons in our chemical reaction. It just depends on the nature of the chemical reaction. And the way to predict that is that long set of rules that you have. So we're basically trying to figure out, if we know this is what happens in our chemical reaction, we put this into our container and we get these out and we can measure that in lab. We want to know what else happened. Did we use H2O up? Did we use protons up, or were we in a basic solution, we had to use some of these up, what happened. And that's what our process is for balancing this equation in a lot of steps. Okay, so here it is. The first thing you want to do, break it down like we just did with our oxidation numbers. And then we're going to break this into half reactions. And the bromine lost 1 electron. The manganese gained 5 electrons. It goes from +7 oxidation number to a +2 oxidation number. And that shows that it gets 5 more electrons per manganese atom. And the bromine loses 1 electron per bromine atom. And when we break these into the half reactions, something's a little bit different in this chemical equation. We have the manganese attached to the oxygen, and the oxygen gets to stay with the manganese when it goes into the reduction half reaction. Anything attached to the element that's getting reduced here gets to go and be part of the half reaction. So you bring the whole element with all the compound attached to it. So we get this. We get an oxidation half reaction and reduction half reaction. And now we need to balance these half reactions. Let's do our oxidation one first. That's our easy one. We want to balance atoms first, just like we did on our simple cases. We have 2 bromines on the right, and we need 2 bromines on the left. So I'm going to put a 2 here. Now my atoms are balanced. I'm going to balance my charge. I have a -2 charge on the left, and I need to have a -2 charge on the right. So I'm going to say +2 electrons. And that's oxidation, losing electrons. We lost our 2 electrons, and here they are. Our reduction half reaction, we're going to do the same thing. We're going to balance it. And the first thing you want to do is balance your atoms. And we have 1 manganese on the left and 1 on the right. But for the first time, we have a problem because we have oxygen involved in this reaction. And your oxygen has to come from somewhere or be going somewhere. And it's going to be these guys. We have oxygen in H2O or oxygen in our hydroxide groups. And here's your method for keeping track of oxygens. If you need more oxygens in a chemical reaction, we're going to use H2O to give more oxygens. And so right now we have 4 oxygens on the left, and we need more oxygens on the right. And H2O can participate in this chemical reaction. So I'm going to say we had 4 H2Os produced in this chemical reaction when the oxygen left the manganese here. And that gives me my 4 oxygens. Now I also introduced hydrogen into this equation, and I introduced 8 of them. 4 H2Os gives me 8 hydrogens. And now I'm going to have to include that on my reactant side. And if this is an acidic solution, I'm going to say H plus here. Okay. And you might label this in your notes here. This is acidic solution. Remember when we talked about this, we had either H plus is available or OH minus is available floating around in solution for my chemical reaction to occur. And we're going to balance this first in acidic solution. And so we get this, H plus is floating around. This is now balanced in terms of atoms. I'm sorry, no it's not. We need 8 of these. And now it's balanced in terms of atoms. We have 8 H pluses and 8 H's on this side. We have 1 manganese, 4 oxygens, and 4 oxygens. Now we want to balance it in terms of our electrons. So let's add up our total charge on the left side here. If you add up your total charge, you have 8 positives and 1 negative. That gives you +7. If you add up all the charge on this side, H2O is neutral, and we get a +2 from our manganese. So the difference in charge here is +7 on the left and +2 on the right. So I need to add here 5 electrons to the left side, so that when I get my +7 and a -5, this adds up to my +2 charge. And now we have equal charge on both sides. So we've balanced our electrons and our atoms. That's your hard part. We've got both those half reactions balanced now in terms of atoms and in terms of our charge or number of electrons. And now we have to figure out how do we add these 2 half reactions back together so that the electrons transferred are equal. We want to give the same electrons as we receive. And we want to get the least common multiple between 2 and 5. And that would be 10. So I'm going to take my oxidation half reaction and multiply by 5. I'm going to take my reduction half reaction and multiply by 2. And if you do that, I'll write out our math here. I'm going to write it one above each other so it's easier to add our equations here. But 2 times 5 is 10. So I'm going to go 10 BR with a minus. Turns into, on my product side, BR2 times 5 would be 5 BR2s. Plus 10 electrons. From my reduction half reaction, I get this. 2 times 5 for my electrons, I get 10 electrons on this side. That's good because these electrons are going to cancel when we add our equations together. I get 2 times 8, which is 16, so I get +16 H pluses. I get manganese, permanganate times 2, so I get +2 MnO4 minus, and there's all my reactants. And that turns into my products, 2 M in 2 plus 4 times 2 gives me 8 H2Os. They're still balanced half reactions because we multiply by a whole number ratio. And now I can add these together to make one overall equation. And my overall equation would be this. 10 bromines, Br minus, plus 10 electrons, plus 16 H pluses, plus 2 Mn O4 minus, turns into my product's 5 Br2 plus 10 electrons, plus 2 Mn 2 plus. We're just taking everything on the product side and combining them, and everything on the reactant side and combining them. And this reaction, I can cancel anything that's the same on both sides, and that's my 10 electrons. And I'm just going to erase it here so I don't rewrite it. So my balanced equation, these are going to cancel. These 10 electrons here and these 10 electrons here leaves me this for my balanced chemical equation. And this is what we would expect to happen in solution for this chemical equation that we started with here. What's actually happening? Well, it's going to be taking in 16 of my acidic protons and combining them with my oxygens here when that electron transfers from my magnesium bromine, and I produce H2O. So this would be my balanced chemical equation in acidic solution. If you want to balance this in basic solution, we can't have H pluses. In basic solution, we only have these OH minuses. So these guys aren't floating around because we're in basic solution. So if we want to do this next, how does this balance in basic solution? You take your equation that's balanced in acidic solution, and all we do is we want to neutralize these H pluses. And we do that by adding hydroxide. And H plus plus hydroxide equals H2O. So I want to add 16 of these hydroxides so that all 16 of my H pluses react and make H2O. And if I do it to one side, I need to do it to the other side. So I'm going to add 16 OHs to this side as well. And this becomes right here H2O. So I get my chemical equation here. I get 10 Br minus plus, instead of 16 H pluses, I have 16 H2Os now, plus 2 MnO4 minus turns into 5 Br2 plus 2 Mn2 plus I have 16 hydroxides on this side, and I have 8 H2Os. And now I have a solution in basic environment. And if you look at both sides of this equation, there's something that can be canceled. These 8 H2Os over here and the 16 over here, I don't need to write 8 of those twice. So these 8 H2Os will cancel 8 of these, and this is my balanced chemical equation in a basic environment. The same reaction could occur in basic solution, and if it does, H2Os are going to be consumed in this reaction and produce more hydroxide. It's going to get more basic. Okay. So try that on your next problem. You have one more example problem in your packet in acidic solution, and then come back to the video here. You can pause it, and I'll show you your solution. Here's your solution for your, right here for your next one. You should have gotten this. You should have gotten the carbon being oxidized, losing 2 electrons. The chromium gains 3 electrons and it gets reduced. If you break that into your half reactions and balance them, your oxidation half reaction looks like this. You should have 2 extra electrons and 2 protons. That allows your 4 hydrogens on this side to be balanced with your 4 hydrogens on this side. Your reduction half reaction looks like this. Balance your atoms first. You would have started by balancing your 2 in front of your chromium because we need 2 chromiums on both sides. I have 7 oxygens, so I need 7 H2Os. That gives me my 7 oxygens. Once you have your H2Os, you want to use your number of hydrogens on this side, which is 14, and add 14 positive protons on this side. That's from your acidic solution. And then add up your total charge on the left and total charge on the right, and you'll find that you need 6 electrons on the left side. Well, the least common multiple between 2 and 6 is 6. So your reduction half reaction, you don't have to multiply by anything, but your oxidation half reaction multiply by 3. If you multiply that by 3 and add those together, you get this black equation down here. So CH3OH, you're going to have 3 of them because we're multiplying that equation by 3, and that goes for everything in this equation. Your bottom equation, you don't have to multiply by anything. You just put those straight in. So all the reactants became reactants on this side. All your products became products. And then we're going to balance it, cancel things that are the same on both sides in this reaction. Your electrons must cancel. That's how we know that we did the electron transfer correctly. So the 6 electrons cancel. You have 6 H pluses on this side that can cancel with 6 of your 14 on this side, and you're left with this at the end of your chemical reaction, and that's balanced in acidic solution. So we would expect in this chemical reaction, some of the acid will be consumed, and we're going to produce some H2O when that electron gets transferred between your chromium and your carbon. I hope that helps, and come to class with questions tomorrow, and I'd be glad to help out.